Great, thank you very much, and a special thank you to the organizers for inviting me to speak. It's really a great thrill and a great delight for me to be here. In this brilliant first talk this morning, Dave has told us a little bit about many of the exciting applications of ultra-cold molecules. So I'll just start my talk by highlighting some of the goals that we are working towards in our group. Starting with this one, it's an illustration of an apparatus that we'd like to build. It's a fountain of ultra-cold Ytterbium fluoride molecules for measuring the electron's electric dipole moment. Okay, so we at Imperial College already use these YBF molecules to measure the electron EDM. At the moment, we do that with molecules at about 4 Kelvin, and if we could cool these molecules to ultra-cold temperatures, then that experiment could become a great deal more sensitive. Another goal that we're working towards is to be able to study collisions between atoms and molecules at low temperatures, and to use those collisions to drive sympathetic cooling of molecules using ultra-cold atoms. And for that application, we're focusing on the calcium fluoride molecule. And then a goal really for the whole field is to take these ultra-cold polar molecules and to organize them into regular arrays, and to use that to study the behavior of such strongly interacting quantum systems. So we're working on the laser cooling of both of these species, Ytterbium fluoride and calcium fluoride, and in my talk I'll concentrate mainly on the calcium fluoride experiment. This is an illustration of the apparatus that we've set up to make a magneto-optical trap of calcium fluoride. It starts here with a cryogenic source, which produces a beam of these molecules, which are then slowed down by counterpropagating laser light and finally delivered to the MOT. So I'll say a little bit about each of these steps here. Starting here with the cryogenic source. So we make these calcium fluoride molecules by laser ablation of a solid target into a flow of helium gas at 4 Kelvin. This produces a pulsed beam of calcium fluoride. The pulses are quite short. They come out at 280 microseconds duration. And the velocity distribution looks like this. Okay, so it's typically centered around 150 meters per second, and it's about 90 meters per second wide. This source produces a high flux of molecules. We measure 1.6 times 10 to the 11 calcium fluoride molecules per steradian per pulse in the first rotationally excited state, which is the state that we use for the laser cooling. Okay, so that's the source, and then I'll tell you now about the slowing and the MOT. The level structure of calcium fluoride is almost identical to the structure of strontium fluoride that we just heard about, and the laser cooling methods that we use are almost identical to the ones that Dave just explained in his talk. So here are the 3 lowest vibrational states in the ground electronic state of the molecule, the X state, and here the 2 lowest vibrational states in the first electronically excited state, the A state. If you put a molecule into this V equals 0 state here in the A state, it decays in the following ways: 97% of the time to V equals 0, 3% of the time to V equals 1, and 0.08% to V equals 2. So those are already good branching ratios, favorable branching ratios for laser cooling. In our experiment, we also use the B state of the molecule. That's the second electronically excited state. And it has even better branching ratios. 99.8% of the time, it decays to V equals 0, 0.2% to V equals 1, and only 0.0015% of the time to V equals 2. This means that actually for the slowing step of the experiment, we actually only need to use 2 lasers. So to do the slowing, the main light that we use is this transition here, the X to B transition at 531 nanometers. And then we repump the population that leaks into V equals 1 using this transition here at 628 nanometers. Okay, so it's just two lasers to do the slowing. For the MOT, we choose to use the X to A transition. So the main cooling light is this transition here at 606 nanometers. And then again, we repump population from V equals 1 using this transition here at 628 nanometers. And we also repump the population that goes to V equals 2 using this transition here, also at 628 nanometers. So there are 3 main lasers to make the MOT. And then a subtlety, which Dave already told you about, is that each of these vibrational states has hyperfine structure. There are 4 hyperfine components, which in the case of calcium fluoride are these radio frequency intervals here. And we have to apply radio frequency sidebands to each of these lasers in order to address all 4 hyperfine components of the transition. And we do that using a combination of acousto-optic and electro-optic modulators. So that's the scheme that we use. We've concentrated a lot on the laser slowing step, so I'll say a little bit about that. So this is the setup that we've been working with for the laser slowing. We detect these molecules 3 times by laser-induced fluorescence detection on these 3 photomultiplier tubes here. This graph is showing you the time of flight profile of molecules passing through each of these 3 detectors. And at each of these detectors, the probe laser that we use for the laser-induced fluorescence detection, it can either cross the molecular beam at right angles, or it can cross the beam at an angle here. And this way, we can measure the velocity distribution of the beam via the distribution of Doppler shifts. Everywhere in the experiment, there's a 5 Gauss magnetic field applied, which does the job of rotating the dark states in the experiment back into bright states. And then we apply the slowing light counterpropagating to the molecular beam. The main slowing light is applied for a 6 millisecond period in this time window here, and the repump light is on for the whole time. Now, as everyone knows, you have to do something to compensate for the changing Doppler shift as the molecules slow down, and we do one of 2 things. We either use a frequency chirp, so in fact, we first of all apply the 4 radio frequency sidebands to the light that we need to address the 4 hyperfine components. And then we take those sidebands and chirp the whole lot up in frequency to follow the changing Doppler shift of the molecules. So we either do that, or we keep everything fixed in time and just spread the frequency of the light out to about 200 megahertz. So then I'll show you some data that we get from these slowing experiments. First of all, the slowing using the frequency broadened light. What I'm showing here on the left-hand side are the time of flight profiles that we measure at this last detector on the left-hand side. On the right-hand side, the velocity distributions that we measure at that same detector. The black curves are what we see when we do nothing, when there's no light applied, no slowing light applied, and the red curve when we apply the slowing light. And this frequency distribution of the light transposed onto the velocity axis is shown by this green curve here. So you see that the light pushes the molecules down to lower velocities, about 100 meters per second in this case. And the molecules also bunch up in velocity. Okay, they bunch up at the velocity where they fall out of resonance with the light. So we have both slowing and cooling in this case. And then as we slide this frequency distribution along, we're able to slow the molecules down to lower and lower speeds. We also have a numerical model that we use to simulate this entire experiment and make sure we understand what's happening. And these curves here that I'm adding are the results of that model. Okay, so you see they match very well, and we have a very good understanding of everything that's going on. So that's the slowing using the frequency broadened light. Now let me show you the results with the frequency chirp. So actually in this very first experiment here, there's no chirp applied to the lasers. The laser is just fixed frequency here, shown by this red dashed line, where molecules moving at 178 meters per second are resonant with the light. And actually already that pushes the molecules down to about 100 meters per second. And again, bunches them up into a narrow velocity distribution here. And now as we apply the chirp, larger and larger chirps, we're able to slow the molecules down to lower and lower speeds. And again, we use the model to check that we know what's going on. Actually, in this case, the model finds some lumps and bumps that we don't see in the experiment, but by and large, the numerical simulation matches pretty well with what we see. Now, you will have noticed, I'm sure, that we're losing molecules here, and the more we slow them down, the more we seem to lose. Okay, and the reason for that is very simple. We're changing the velocity distribution only in the forward direction. We do nothing at all to the velocity distribution in the transverse direction. So the molecules, as they slow down, they just diverge more and more and more. And it's less and less likely that those slow molecules will pass through the small detection area that we have. Okay. And as far as we can tell, we've investigated this, as far as we can tell, that's the only source of loss that we have in the experiment. This problem of the ever-increasing divergence actually made it very difficult for us to even see molecules much below 50 meters per second until we changed the experiment in one crucial way. So all of these data here were taken with a collimated laser beam, and we then changed that to a converging beam, a beam that converges towards the source, the molecular source. And that adds a small component of transverse cooling to the molecular beam. And as soon as we did that, we were able to see molecules at much lower velocities. So here's some data where we now using this converging beam and increasing the frequency chirp further, we were able to slow molecules down to 15 meters per second. And this bunch of molecules here contains 8 times 10 to the 5 molecules per square centimeter per pulse, passing through the plane of our detector. This velocity, 15 meters per second, we think it's low enough to be able to capture into a magneto-optical trap. And so now I say a little bit about that. In his talk, Dave explained already some of the problems that you have in the molecule MOT that you typically don't have in a normal atomic MOT. So one is that for the molecules that most people are working with, the G factor of the excited state is very close to 0, so there's hardly any Zeeman splitting in the excited state. And in a normal MOT, you cannot make a normal MOT when there's no Zeeman splitting in the excited state. That's one problem, and then a second problem is the problem of the dark states. Basically, the molecule goes dark to the MOT beam that is pushing in the right direction and can only be taken out of that dark state by the MOT beams that are pushing in the wrong direction. Okay. And then Dave also showed us the gold-plated solution to that problem, which is this beautiful RF MOT. I want to show you another possible solution to the problem, which I call the dual frequency MOT. Okay, so what I'm showing you here is a system f equals 2 in the ground state and f equals 1 in the excited state, and no Zeeman splitting in the excited state. This system has both of those problems. Okay, there's no Zeeman splitting in the excited state, and there's dark states here in the f equals 2 to f equals 1 system. And the idea is to drive this MOT with 2 frequencies, one which is red detuned and another which is blue detuned. And the 2 frequencies have opposite circular polarization. If you now think about what happens to a molecule which is displaced to the right of the MOT, and we suppose that it's in the m equals plus 2 state, okay, it's in plus 2 state, and so it can only interact with a sigma minus beam. And there are 2 sigma minus beams, but the one that's red detuned is the one that's closest to resonance. So it's most likely to be driven by the light here, which is pushing back towards the center. And similarly, if we take the molecule in the m equals minus 2 state, it can only interact with the sigma plus beams, and there are 2 sigma plus beams. But now the one that's blue detuned is the one that's closest to resonance. So again, the beam that pushes back towards the center is the one that is interacting the most. So this looks like it ought to work. To check whether it does work, we've done some complete numerical simulations of this sort of MOT. And so I'm showing you here the trapping frequency. What I've done here is I fixed delta 1, the detuning of the red detuned light. I fixed it at minus gamma, and then I change the detuning delta 2 and plot the trapping frequency as a function of delta 2. Positive values mean that you have a trap. Okay, so what you find is that indeed on the blue side here, you expect to have a trap. And in fact, for some values on the red side, you also have a trap. But the blue side is better as expected from the picture. That's the trapping frequency. We also need damping, of course. This is the calculation of the damping, where positive values mean you have cooling. And now if you take these 2 graphs together, then you see that in both of these regions I've shaded green here, it should be possible to make the MOT. And I'm highlighting this particular mechanism because actually it turns out you basically get this for free in these molecule MOTs of calcium fluoride and also strontium fluoride. So to illustrate that, here again is the level scheme for calcium fluoride for the main cooling transition, showing you the 4 hyperfine components of the cooling transition. And now I've plotted the Zeeman splitting of the states. So the excited state has almost no Zeeman splitting. The ground states have Zeeman splitting like this. And now to make the MOT, of course, it's natural to apply red detuned light to each of these transitions. That's what I've done here. And then you see the subtlety is that this one component is polarized oppositely to all of the others. If you do that and concentrate on this upper system here, the F equals 2 system, you see that it's exactly the one that I illustrated on the previous slide. So this F equals 2 state is being driven both by red detuned and blue detuned light of opposite circular polarization. And this part of the scheme here should provide the trapping and cooling forces. Does this work? Again, we've done the numerical simulations of this system. And what I'm plotting here is the acceleration versus the displacement from the MOT center, and the acceleration versus the speed. And the upshot is that this should work very nicely. We predict a trapping frequency of 160 hertz and a capture velocity of 20 meters per second. Okay, so that's where we're up to. So we've built our MOT based on this idea. The apparatus is set up. We have slow molecules arriving in the MOT region, and we are right now in the lab searching for our very first MOT signals. All of this has been about calcium fluoride. Let me just say one brief thing about ytterbium fluoride, which we're also working on. So YBF is a more difficult beast. It's much heavier, which means you have to scatter a lot more photons. And those branching ratios are not so favorable, so it's more difficult to scatter a lot of photons. But we set up this experiment where we try to apply transverse laser cooling to a beam of YBF. Okay, so here the beam is going up in the vertical direction, and it passes through this 20-centimeter long region of transverse cooling, and then we see the molecules by laser-induced fluorescence on a camera here. And so I show you here our very first data. It's just from a few days ago. Again, the molecules are going up, the laser beam crossing horizontally, and where the two cross, you see this stripe of fluorescence from the molecules. And then you notice there's a bright spot in the middle. Okay. When we apply the laser cooling light, there's a bright spot in the middle. If you take the cuts, then we see this. Okay, so here, when we apply the cooling, we see this broad distribution of molecules, and on top, this narrower distribution, which is probably the first evidence we have for the transverse cooling of these molecules. So this is all highly preliminary, very early data, but we're excited about this because this looks to us like the very first step of being able to do an electric dipole moment measurement using laser-cooled molecules. Okay, so then in the last few minutes, I want to say something about polarization gradient forces and their likely role in a molecule MOT. What I've plotted here is our calculation of the force versus speed for a molecule on using this F equals 1 to F equals 1 system being driven by red detuned light. Okay, and the calculation is done in 3 dimensions in the standard MOT configuration. So what you see is that at high velocities, you get the normal Doppler cooling curve, okay, a negative force, so you have damping here. It's just the normal Doppler cooling. But at low velocities, the force goes positive. Okay, so these are the polarization gradient forces acting here at low velocity, and they, in this particular case, are a kind of anti-damping force. If we zoom into this low velocity region here, this is what it looks like for the 2 standard configurations that people normally think about for subdoppler cooling, okay, the sigma plus, sigma minus, and the lin perp lin configurations. So there's a place here, there's a particular velocity here where the polarization gradient force cancels the Doppler cooling force, and the system will be driven towards this equilibrium velocity where the force is 0. And actually, if you put in the numbers for calcium fluoride or indeed for strontium fluoride, you find that this equilibrium velocity for these particular parameters here, it's very high. Okay, it's about 2.5 meters per second, which is the mean speed of a 17 millikelvin distribution. Okay, that's 2 orders of magnitude hotter than the Doppler cooling temperature. This calculation was done for an intensity of the saturation intensity in each of the 6 beams. If you lower the intensity of the light, then this equilibrium velocity V0 moves down towards lower speeds. Okay, and in fact, the relationship is a very simple one. We find that the square of V0 just scales linearly with the intensity of the light. Okay. And again, if I put the Doppler cooling limit here for calcium fluoride on this same graph, it's all the way down here. Okay, This graph here, I hope, is reminiscent of the temperature data that Dave showed you for strontium fluoride in his talk, right? What he indeed finds is that at high intensities, the molecules are heated to temperatures that are much, much higher than the Doppler cooling limit. But then as the intensity is reduced, the temperature comes down pretty much linearly towards the Doppler limit. Okay, so I put this out there as at least a plausible explanation for that observation. Now, you might object that these polarization gradient forces are normally very strongly suppressed in the presence of the Mott magnetic field. And so we looked at that. What I've plotted here is this peak force here, okay, the peak of the polarization gradient force as a function of the applied magnetic field. And we look at it, first of all, for the F equals 1 to F equals 2 system, where there are no dark states, the kind of normal system that you would choose. And indeed, we find that this peak force falls off very, very quickly as a function of field. That's very well known. But now if you do the same thing for the 1-to-1 system, or indeed any of the systems where there are dark states, we find that this force is robust to magnetic fields over the entire range of magnetic fields that the molecules experience in the Mott. Okay, so it looks like this mechanism really will be active in the Mott. So to conclude that, then we find that for a red detuning that we have here, polarization gradient forces drive molecules towards this non-zero equilibrium speed. The square speed is linear in the intensity. This mechanism is robust to magnetic fields. And of course, if you turn it around and go to blue detuning, then it seems like these polarization gradients should be effective at cooling to sub-Doppler temperatures, as indeed they do in the standard gray molasses technique for atoms. Now, this calculation was done in 3 dimensions, and to try to understand a bit better the mechanism that is operating here, it's natural to simplify to 1 dimension. If you do that for this F equals 1 to F equals 1 system, for either of these standard polarization configurations, you just find that the force is equal to 0 for all speeds. Okay, and so it seems to offer you no insight into what it is that's happening here. So the 3D case seems to be very, very different to the 1D case. Okay, but in fact, a 1D model can offer some insight into what's happening here. And the model that we need, I think, is this one. So again, I have the 1-to-1 system. I drive it now with blue detuned light so that we can see where the cooling should come from. And the two counterpropagating beams, I take them to have linear polarization with an angle phi between the 2 states of polarization. Okay, so phi equals 90 degrees would be the standard lin-perp-lin configuration, but we keep this general angle phi here. This system has been studied long ago in the literature. So what does this look like? Okay, you get, of course, a standing wave of intensity. I do it here for an example where phi is 45 degrees. So you get a standing wave of intensity, but the intensity never goes to 0, and the polarization is changing as you move through this standing wave. In this F equals 1 to F equals 1 system, of course, there are dark states, or there's a dark state. There's a dark state and a bright state. And if we plot the light shift of the bright state, then it looks like this. Okay, the light shift is greatest where the intensity of the light is highest. And then, of course, there's a dark state which has no light shift. A molecule that starts out in the bright state will be very quickly optically pumped into the dark state. And that's most likely to happen where the intensity is highest, here. Okay, and now the molecule is in the dark state, but it's moving through this changing polarization. Okay, so there's some probability of a non-adiabatic transition back onto the bright state. And that probability is maximized here where the 2 states approach each other. Okay, so a molecule will tend to follow this sort of trajectory, like this. And you get, of course, a Sisyphus cooling mechanism. Okay, so this is a Sisyphus cooling mechanism, but it's a bit different to the normal mechanism that you normally think about, which only involves optical pumping between states that are differently light shifted. Here you need both optical pumping and this non-adiabatic transition between the 2 states. And now you see that if you put phi equal to 0, the force will vanish because there are no polarization gradients. If you put phi equal to 90 degrees, that's lin-perp-lin, the force vanishes again because in that case there are no intensity gradients. But for all other values of phi, there's a force. And I'm highlighting this because now if you go back to the three-dimensional case, even for the standard polarization configurations, and think about a molecule or an atom moving in some arbitrary direction through this three-dimensional light field, in general, it will be seeing gradients both of intensity and of polarization. And so this mechanism here ought to be operating. Okay, so that brings me to the end of my talk. So finally then, let me thank all of the excellent people who have been working together with me on these things. And finally, thank you all for your attention.
Thank you, Mike, for this very exciting talk. We have time for a few questions. There is one in the back there. So I have one, just one. Could you show you the small laser cooling that you've shown, in the transverse beam of YB? Because you showed a narrow peak, but the signal with no laser was higher. So without cooling and with cooling,
yes.
So it's lower. So how can you claim that this is not a force which does not act at zero velocity on this graph?
So I guess I'll repeat again, this is very, very early data, and you're quite right that when we apply no cooling, we see a higher signal. Now, actually, this is what we expect. Okay, so in this particular case where we have just these three wavelengths, we expect to be losing some molecules. So there's optical pumping here into states that we never detect in the detector. So in fact, we expect it to lose about 50% of the molecules, which is roughly what we see. Okay. But of course, you're quite right that somehow until we repump those and we actually see this bright peak sticking above what we had previously, then it's really hard to claim anything. On the other hand, we've sort of thought just a little bit about other possible mechanisms that might give you something like this. And actually, we can't find anything that gives you something so narrow. Okay, the only thing that seems to give you such a narrow peak here is the cooling. So I don't want to say too much, but that's what we currently know.
Other questions? Yes.
So you and Dave talked about laser cooling, but there is also a stock decelerator and electrostatic quadruple lens type of a stock force. Is there a way to combine those features and your laser cooling scheme to get a better performance?
Yes. So actually, one of the difficulties that Dave already alluded to, one of the weak points, if you like, is actually this slowing step. Okay, so it tends to be that the step of slowing the beam down to low velocities is quite inefficient. And so it's certainly possible to use a Stark decelerator or a magnetic decelerator or some other kind of decelerator that's been invented in this field to do that slowing step. And now, they also tend to be very inefficient, okay? They typically take a very, very narrow slice of the phase-space distribution that you start from and slow them down. But it is possible to think of, first of all, applying some transverse cooling to compress that phase-space distribution and then inject that into a decelerator of some kind to slow the molecules down. So we are thinking about that, and I think others are thinking about it.
Another question? Yes?
What's the time scale for the B state of calcium fluoride decay to the A state? Do you know?
The lifetime of the B state?
The decay from the B to A.
The B to A, yes, thank you. That's a nice question. So we really worried about that, okay? So there's actually a very obvious leak via the decay chain B to A to X, which actually takes molecules out of the cooling cycle. See if I can find it. Yeah, so so the B state can decay to the A state, which then decays to the X state, and that takes molecules out of the cooling cycle because it puts them into a rotational state that we don't address. Okay, we were worried about that. But what we find in the experiment is that that leak is actually smaller, even smaller than this leak to V equals 2, right? It's smaller than this 0.0015%. So it turns out not to be a problem in the experiment.
Okay, we have time for one.
Oh,
one
sorry,
last.
I have a continuing question. So that means it's comparable to the V equal 2 state decay. So that's why you are not doing that for the MOT?
That's right. It's actually, the branching ratio is actually half of this decay here. Okay, so it's a half of 0.0015%. That's the branching ratio.
I see no more question. I have just a remark. I mean, the lin-theta-lin configuration that you showed does lead to a magneto-optical trap on alkalis. We had a paper in '92 about that. You know, the same scheme that you've shown in 1D. It's very, very efficient actually. Also, it traps atom even in 3D.
The F equals 1 to F equals 1 system to make.
No. We tried it on JJ plus 1, but. With no circular polarization whatsoever, just lin-theta-lin in all 3 dimensions.
Okay, right, to make a MOT.
Yeah.
Right, I mean, actually, you know, the history, if you look at the history, which you probably know better than me, then of course, you know, the very first MOT paper already investigated the MOTs driven on the sort of what we now think of as the normal transition, and also on these transitions with the dark state. So even there in the very first paper, it had been studied.
Okay, so I think we have to move on. Let's thank Mike again. And the last talk of this cold molecule session is by Simon Cornish from Newcastle, Durham. And he will speak about coherent control of ultra-cold rubidium cesium molecules.